An X-ray halo nearly 400,000 kilometers wide, recorded over 17 continuous hours, placed 3I Atlas into an unprecedented category. No known interstellar object, neither Oumuamua nor Borisov, has ever displayed anything like it. Images from XRISM confirm that this visitor is breaking patterns while simultaneously changing color, accelerating its trajectory, and revealing a composition that goes far beyond ordinary ice. Officially, NASA classifies it as a comet, but the probabilities and the data tell a story that is difficult to reconcile with that simple explanation. To obtain the first X-ray portrait of an interstellar object, XRISM, the Japanese Imaging and Spectroscopy mission, began observations on November 26, 2025, keeping the target under surveillance until November 28th. 14 precise attitude adjustments were required, with constant recalibrations to keep 3I Atlas within the field of view as it moved across the constellation of Virgo. Any error, and the object would have vanished from the frame. At the core of the observation was the X10 Soft X-ray imager, designed to capture extremely faint emissions. The team filtered out cosmic noise, diffuse sunlight, and background emission from the Milky Way, applying a rigorous data pipeline to isolate the real signal. The result was unequivocal: a diffuse glow about 5 arc minutes wide, equivalent to roughly 1/3 of the distance between Earth and the Moon, emerging from the nucleus in a single continuous dataset. JAXA verified the signals, ruled out instrumental artifacts, solar wind contamination, and detector failures. The phenomenon withstood every check. The XRISM dataset now becomes a reference record, open for reanalysis by any team in the world. The detection is real. The mechanism behind it is not. For decades, only solar system comets have exhibited X-ray emissions, and even then, never on this scale. With 3I Atlas, something entirely new emerges: a ghostly X-ray mantle extending hundreds of thousands of kilometers beyond the nucleus, defying everything expected from an interstellar visitor. This single detection instantly redrew the limits of what is possible for interstellar comets. The historical record is clear. Oumuamua, the first interstellar visitor, showed no X-ray activity at all, not a single photon above background. Borisov, the second, appeared to be a classic comet in every other respect, yet still failed to register X-ray counts despite deep exposures by Chandra and XMN Newton. All archival and instrumental records remain empty. For 3I Atlas to break this sequence, verified by a 17-hour observation with multiple passes and independent noise and background checks, raises questions that go far beyond a single comet. The central point is not just the brightness itself, but what it implies about the environment around 3I Atlas. The X-ray emission likely arises from charge exchange, a process in which solar wind ions collide with neutral cometary gas, stripping electrons and releasing energy. This is common in active comets, but it has never been observed in an object traversing the solar system from interstellar space. Now, the scale, roughly 400,000 kilometers across, suggests an enormous gas cloud, far more extensive than anything seen around Oumuamua or Borisov. This is not merely a technical milestone. It challenges every model based on those earlier cases. With the XRISM dataset now public, astronomers worldwide are racing to confirm, dissect, and explain the glow. Multispectral campaigns are being organized to observe 3I Atlas across all possible wavelengths, searching for clues in the chemistry and structure of the coma. The question is not whether the X-rays are real. The data indicate they are, but what kind of object can produce them, and why its predecessors remained silent. Hubble's first look at 3I Atlas occurred in July 2025, just weeks after its discovery. The images revealed a classic cometary coma, a diffuse envelope facing the sun, but with one striking difference. Instead of the rounded, symmetrical glow expected of a typical comet, the coma stretched into a teardrop shape, with the tail sharply elongated along the object's trajectory. Over the next 4 months, as the comet approached the sun, periodic Hubble observations mapped a dramatic transformation. By November, the coma had elongated and narrowed. The head intensified in brightness while the tail fanned out behind, tracing a distinct arc across the sky. The entire structure appeared to rotate, with the leading edge becoming sharper, as if sculpted by an invisible wind. Each new frame told a story of change. The teardrop profile did not merely grow, it evolved. The front edge of the coma became more defined, while the trailing material appeared to split, forming subtle ripples and filaments suggestive of turbulent flows. In some exposures, faint striations hinted at localized jets or outbursts, but the overall pattern remained consistent, a body shedding material at a furious rate, yet with a geometry that defied the norms of solar system comets. Hubble's image from November 30th captured the coma at its most dramatic moment. The nucleus, still unresolved, remained buried within a luminous wedge of gas and dust, its boundaries sculpted by sunlight and the solar wind. The tail curved in a broad arc, with brightness gradually fading into darkness. The scale was staggering, hundreds of thousands of kilometers from head to tail, with the coma's width increasing even as its total water content, according to other instruments, remained unusually low. This visual paradox, an object dry in compositional terms, yet hyperactive in every morphological measure, forced astronomers to reconsider what drives such displays. The evolving teardrop shape, mapped in detail by Hubble, became more than a curiosity. It was a clue. The physics at work around 3I Atlas may not fit the standard playbook. The shifting contours of the coma, the asymmetric brightness, and the persistently structured tail pointing to a process both familiar and alien. With each new image, the enigma deepened. How can such a dry comet put on such a vivid spectacle? The James Webb Space Telescope and infrared spectrograph locked onto 3I Atlas just as the comet passed inside Earth's orbit, and within days the numbers began to arrive. Instead of the water-rich signature that defines nearly all solar system comets, the Webb team found something completely different. The spectrum was dominated by carbon dioxide, accounting for 87% of the measured volatiles, with carbon monoxide adding another 9%. Water, the usual engine of cometary outbursts, barely registered at just 4%. For comparison, comets from our own solar system typically show water as the primary component, often exceeding 70%. Here, the balance was inverted. Webb's mid-infrared detectors also identified metallic lines in the gas plume, and the ratios were off-scale. Nickel exceeded iron by a wide margin, a reversal of what is normally observed in solar system comets. In the official plots, the nickel-to-iron ratio stood out as a clear outlier. According to Avi Loeb of Harvard, this pattern is familiar in certain industrial nickel-based alloys. Most planetary scientists caution against jumping to conclusions. Still, the numbers are unambiguous, more nickel than iron, and a level of dryness that places 3I Atlas in a category of its own. The Webb team published their preliminary results in early December, with graphs showing the sharp carbon dioxide peak and the suppressed water line. The shape of the spectrum was unmistakable. This was not a calibration error or solar contamination. Cross-checks with Hubble and ground-based observatories confirmed the chemical profile. Even in the broader context of interstellar objects, nothing like this had been documented before. Oumuamua released almost no gas at all. Borisov behaved like a classic water-rich comet. 3I Atlas, by contrast, was releasing carbon dioxide in record quantities, with an energy budget that did not add up. And that raises a central question. How can an object with so little water sustain such an extensive X-ray glow and a hyperactive coma?